Hello everyone. Today we'll be talking about point accepted mutation matrices. Now, before getting into understanding this, let's start this with an example. Let's say you have X and Y, each one of them having 1,000 amino acids. And your aim is to get the best possible alignment of these two sequences. For the best possible alignment, what do? Put this in a software. And the moment you put this in the software will return saying that which matrix should I use? Because in the due course of aligning these two sequences, I have umpteen number of alignments. And to get the best alignment on screen for you, I need to score these alignments. To score these alignments, what is the matrix that is to be used? Right? That's what it says. Now, let us say you tell the software that you'll have to use a PAM 1, right? Now, listen to me very carefully. When you say PAM 1, the number that is attached here, 1 stands for 1 mutation for every 100 amino acids. For every 100 amino acids. Now, for us to best understand this, the moment you tell the software it's PAM 1, what the software has to do is it has to construct a 20 by 20 matrix. Means you have alanine, valine, lysine, isoleucine, alanine, valine, lysine, isoleucine, 20 amino acids this way and 20 this way. And each of the boxes need to be scored. And based on this value here, your alignment of these two will be scored to give the best possible alignment. So now, the moment you tell the software it's PAM 1, what the software does is it just picks up the sequences in the background. You should remember that there are database sequences that are available in the background of a software. So in the background, it'll pull out sequences that are 85% similar. 85% similar. So it'll align those sequences. Let us say alanine, valine, lysine, isoleucine, and likewise the alignments, alanine, valine, lysine. I'm just taking some arbitrary example. Now, look at this sequence. When it aligns all these sequences, right, all these amino acids across all the sequences, one against the other, right, it ensures that there is 85% similarity. Means 85 out of 100 are similar. Means if you consider 100, 85 of them are similar, one against the other in the alignment. Now, look at this very carefully. Out of the total alignment that you have the total alignment here, right, of all the sequences, whatever be the length, right, all the sequences. When the moment you say it is PAM 1, out of the entire length of this alignment that it has constructed for 85% similar sequences, right? And remember, I forgot to tell you, this alignment is a global alignment. The moment it does, right, you have a global alignment here. out of the total length that you have, it will pick out those chunks of sequences that differ only 1 in 100. Means they're almost 99% similar. See, the total sequences that you have picked up are 85% similar. Out of this, it picks up the chunks of sequences that are similar to an extent of 99%. Remember, PAM1 means one mutation, means they're 99% similar. So that's what. See what, that's why I had written it like this. If you look at this position, all of them have alanine, right? And if you look at this position, all of them have valine. And if you look at this position, all of them have lysine. And there's only one position that is differing, and there's only one mutation. What is that mutation? It is isoleucine to valine. And all the rest of the sequences across the 100 base pairs, right? 100 base pairs, that chunk you are considering, they're all similar. But for this position, which is having one single mutation for every 100. Is that clear? Now you have several chunks, right? This is one chunk. You'll have a second chunk where you have a second chunk where you might have some other mutation out of 100. It is not alanine versus valine, but maybe you have alanine versus valine here across, right? And this is the only piece, only amino acid that is varying, and all the rest of the sequences are similar. Is that clear? So it picks out of the entire set that you have aligned, it picks out chunks where you have 1 in 100 base pair, remember. And after picking out, it will then calculate the probability. What is the probability among these chunks that alanine is always matching with alanine, right? It has a value here. And similarly, it will again calculate what is the probability that alanine has got substituted with valine, like what I had shown here in the second chunk. And similarly, what is the probability that this alanine got substituted to leucine, similarly to isoleucine. And likewise, it will calculate. Let us assume some arbitrary values. We'll assume that the probability that alanine gets substituted with valine is 80%, and the probability that alanine gets substituted with lysine is only 40%. Now, alanine matches with alanine in the chunks of sequences that are there, like just because this alanine matched with valine as well, it will not be 100%. It will now be something like 99%, because you have 100. Out of that 100, at one particular position, alanine is now also matching with valine. Ideally, alanine should always have matched with alanine to get 100% over here. Is that clear? So now what it does is, for all the 20 by 20 amino acid matrix that you have, it will pick out all these chunks that you have, right, for 1 in 100, and then we'll calculate the probability with which the alanine is matching with alanine, alanine is matching with valine, alanine is substituted with valine, not matching. Alanine substituted with valine, alanine is substituted with leucine, alanine is substituted with isoleucine, and likewise it will give you the probabilities. And out of these probabilities, the one with the maximum probability, let us assume that 99 is the one with the maximum probability, it will convert that into log of odds. And once it converts that into log of odds, what it does, it gives you a positive score. Gives you, let us say, a +8. Is that clear? And if the probability is quite low, and you know that the probability is quite low, then what happens? It will get a negative score as well. Like, let us say, if there is an amino acid R here, alanine with R, let us say the probability is 2% or 1%, then it will get a negative score. So that's how the matrix is entirely scored across, but 20 by 20 length, and row-wise and column-wise, and you will get all these values. Once you get these values are put across in the alignments that are already made in the software. And by looking at the score, the alignment having the best score will be thrown onto the screen as the best alignment. Right. That's what you have understood? No. Let's say instead of considering PAM1, you have considered PAM30. What happens? For us to better understand PAM30. Now, again, the rationale is one and the same. What it does, it picks up all the sequences here. Originally, the one that was given by Dayhoff, right? They explained that global alignment is always done, be whatever be the number, right? PAM1, PAM30, or whatever it is. Global alignment is always considered for sequences that are around 85% similar. So it will take out again the globally aligned sequences that are there in the background, and it will again pick up chunks. Now it will pick up chunks which will differ in 30 amino acids for every 100. And within that chunks, again, it will calculate the probabilities of, again, alanine matching with alanine, alanine matching with valine, alanine matching with lysine, or whatever it is. And then it will give you the scores. The probabilities are again converted into log of odds, and then you'll get the scores. So this is how finally what happens is, whatever be your PAM, 85% globally aligned sequences are considered, and then finally a matrix is constructed, and the values in the matrix are used for your further scoring of your alignment. Understood. So this is as far as a practical example is concerned. But what exactly is happening in the background of the software is, see, it is only being done for PAM1. The probabilities are usually calculated for PAM1 alone, right? And then if you want to do it for all the others, all the others are generally extrapolated. Generally extrapolated. For example, if you say a PAM2, if you say it's a PAM2, what exactly is happening is, it's not again going back to that 85% sequence, 85% similar sequences that were globally aligned and looking at chunks looking for 2 out of 100. It's only to make you understand that I told you it looks at 30 out of 100. It's now looking at, right, if once it does PAM1, automatically PAM2 is extrapolated. And how is PAM2 extrapolated? You have the matrix for PAM1, and this matrix for PAM2 is just multiplied, M square. And similarly, even for PAM 250 and for PAM 100, right? Everything is extrapolated from PAM 1, right? PAM, you are asked to calculate for PAM 2, I have already explained, you multiply PAM 1 twice. If you're asked to do it for PAM 30, this PAM 1 matrix is multiplied 30 times. And similarly, your PAM 250 now, if you're asked to calculate or find out the substitution matrix, what the software does is it multiplies PAM1 to the power of 250. We'll discuss about Blossom in the next class and how it is different from the PAM. We'll go back to our text here. Point accepted mutation, first given by Margaret Dayhoff. And this entire matrix calculation is based on global alignment of sequences that were 85% similar. That's what I told you, right? Remember, hopefully. Now, when we selected PAM1, what did we do? We selected chunks out of the entire length of sequences that were 85% similar. We picked out those chunks that had one mutation for every 100 amino acids. It means those chunks were quite similar to an extent of 99%. So whatever is your probability that was calculated based on the background sequences that were quite similar. So it means for a lower PAM, you can best compare sequences X and Y if they are assumed to be closely identical or similar. If you take a lower PAM. And if you take a higher PAM, let us say for PAM 30, what did we have in the previous written part? We saw that out of the entire 85% globally aligned sequences, we have picked out chunks that were having 30 mutations for every 100 and then calculated the probabilities. So as the number increased, right, what happened? You are picking out chunks that were more divergent within that entirely globally aligned sequences to calculate your probabilities. So this number will indicate the divergence. Ultimately, it indicates the divergence. So for a higher PAM, if you are looking at, it means that you are calculating the probabilities by having divergent sequences in the background. So ultimately, you expect that this higher PAM values that were calculated for the substitution matrix can be best used to compare X and Y if they are not that closely related as they were here for PAM 1. So as the number increases, means for more divergent sequences that you want to compare or you want to align, you'd be using a higher PAM. And for lesser divergent sequences you want to compare, you'll be using a lower PAM. Thank you. We'll be talking about block